So there'll be T at 4 in Atlantic 2117. Yes, it agrees with this piece of paper, so it's definitely happening for postdocs and graduate students. So Ofer obtained his PhD from Technion in Israel. He also worked at this quantum technology lab of the Israeli company Rafael. So, he was studying quantum memory, sensors, and atomic physics and hot vapor systems. Then he did his postdoc research at Harvard and MIT, where he studied photon-photon interactions and ultracold atom systems, perhaps similar to what he's going to tell us today. And since 2014, he's been running a light matter lab at the Weizmann Institute, where he studies quantum linear optics with Rydberg atoms, such as this, along with quantum memories and quantum-enhanced sensors. Ofer has won numerous awards, including the Bessel Research Prize by the Humboldt Foundation and the Krill Prize for Excellence in Scientific Research by the Wolf Foundation. And today he will tell us about quantum vortices of photons. Please, Ofer. Thanks for.
All right. Thanks, Alexei, for the invitation, and thank you all for coming. So indeed, we're going to talk about quantum vortices of photons and about interaction between photons. And what I decided to do here right in the beginning for the next few slides is actually to run through kind of an overview, the jargon, the language, so that we rush to the end, we understand what these vortices are, and then we slow down and go kind of backwards to a more decent introduction. So bear with me. So generally, our system will look something like that. We have some ensemble, an atomic gas. We use ultracold gases of rubidium. That would be our optical medium. And then we send photons in one dimension along this ensemble from one side to the other, and we measure these photons on the other side. And we want to get these photons to interact strongly. We will define what it means. And the way we do that is that when these photons propagate inside the medium, they propagate much more slowly. They couple strongly to the atoms, and they excite the atoms to an excited atomic state. And we use Rydberg states with principal quantum numbers that go up to even n equals 100 and even above. And that means that now our photons that propagate as polaritons, each of these photons carry on its back an antenna, a very strong dipole. And for two photons, that means that these photons will strongly interact inside the medium, effectively interact. And of course, the photons themselves do not interact. What interacts is the atom component of those polaritons. That will be our system. The interaction between Rydberg atoms, as probably most of you know, is very strong because it scales very fast with the principal quantum number. And if we use the van der Waals interaction, it scales as n to the 11. And therefore, we get a very strong, a decent interaction at distances that are even longer than the wavelength. So at distances that are on the order of 10 microns, which if you are familiar with the Rydberg blockade, that's usually the radius of a Rydberg blockade volume. We can already get a substantial interaction between the photons. So we can manipulate on the optical level the structures that come up from this interaction. When we envision what happens to the photons, we use this construction that we call the two-photon or the few-photon wavefunction. That's almost like a wavefunction of matter. It's actually the probability amplitude to find the photons inside. And if we have two photons, that would be the complex amplitude of finding at time t, one photon at coordinate z1 and the other photon at coordinate z2. And if you want a more formal definition, that would be the amplitude here. So here we have 0 photons in some particular space-time window. Here we have only 1, and here we excited 2 at coordinate z1 and z2. So that's the creature we are talking about. This is the creature that will also hold these vortices that we go to. When we measure the photons usually outside of the medium. It's hard for us to measure these photons inside. And therefore, what we do, we put detectors outside. We learn about the statistics of the outgoing photons. And from that, we want to infer what happens inside. So for example, we could measure the intensity correlation function, the normalized intensity correlation function, the well-known G2 function, which is a function of the detection times T1, T2 of these photons. And this tells us something about the probability of finding two photons at some distance between them, which we could associate indirectly with the absolute value squared of our wave function. Okay, so there is some kind of reverse engineering or some dynamic that happened between the inside of the medium and then the outside of the medium. And we can also measure something that is related to phase, which we call the conditional phase or the nonlinear phase. We simply split the photon before it enters the medium. We compose an interferometer, and we could extract the accumulated phase of one photon in the presence of another photon at some distance in time, which we can somehow relate to the argument of the wave function, and therefore try to reconstruct the full complex wave function. All right? Okay. Now, how does this look? So because we have two photons and two coordinates, we can plot them on a two-dimensional space. Remember, this is not real 2 dimensions. This is a one-dimensional system with the coordinate, with the first photon inside the medium being somewhere between 0 and L, and the second photon being somewhere between 0 and L. And therefore, we get all of those options where either both photons are still out. What we do usually is we send laser light inside the medium. So we take our narrow band laser, we put many, many dark filters in front of it until it really becomes weak. This is a weak coherent state with some Poissonian distribution, and this is sent to the medium. So here the light is classical Poissonian. Then one photon could enter, or the other photon could enter the medium, but only when the two photons are both inside the medium, which is the black part, this is where they interact. So most of the fancy stuff happens here inside. And inside the medium, because we have a polariton, each of these photons would be a superposition, or this polariton is a superposition of either being a photon or being a Rydberg atom. So we need to follow two different amplitudes. We either have two photons, one is coordinate Z1 and one in coordinate Z2, or the photons that is already inside could excite a Rydberg atom. So then there is the amplitude of getting, one photon and one Rydberg atom.
Okay, so I'm a little bit confused.
Mm-hmm.
This is a weak coherent state.
That's correct.
I mean, usually I think of such a thing as being a superposition of a bunch of Fock states.
That's correct. Yeah, maybe we can even
spatial mode.
Here it is, right?
Right, exactly. But then, but the picture you keep showing of this two-photon wave function, it's like the two photons are
two photons.
Separate places. But if they're
so
if this was a coherent state in a single mode, then it doesn't seem like it should look like that.
So first, when you say single mode, let's agree that we are saying a single spatial mode.
Yeah.
All right. And then temporally, we could find a photon somewhere. So we have a lot of those temporal modes, right?
Yeah.
And then because this is a very, very weak coherent state, this part of the superposition would be dominant. Right. There would be a lot of zeros. All right. So within a time bin, within a temporal mode, a slice of this temporal mode, I would say that we rarely get a photon.
Yeah.
Then we have this a subspace of having one photon, right. And within the subspace of having two photons,
which is very small.
It's very small. But if we narrow down our view only on that, and if we focus only on that, we would have a symmetric functions in here, right? To find these two photons somewhere within the subspace we opened. So in that particular case, in this example that I gave, with one of the photons could excite and one of the one is always a photon, the other one could excite a photon. We have two options in here, right? Two probability functions in here, and because these are indistinguishable photons, these are the same mode, yeah. They must be symmetric functions, and that's it. But we do have the freedom, in a sense, to have a structure in here. This structure could have, it could be a function Z2 that generates a two-dimensional, structure.
Size, you want to just the product of like H of C1 times H of C2, where H is the shape of your pulse.
As long as there are no special correlations, quantum correlations, this would also always be a product state of the two, single photon shapes or whatever it is.
But it would have to be. Well, I'm just trying to think of what would be the the situation. If I detect a photon here, then I'm most likely to detect the second photon. If there is a second photon, I'm most likely to detect it over here.
There would be many options.
It
It might be that the correlations are positive, and then if you detect one, you most likely detect another one soon. It might be the opposite, that you are now detecting an anti. Right, the input is a coincidence, therefore in the input, those correlations will simply be zero. And then they develop those correlations, anti-bunching or bunching, when they start to effectively interact inside.
Okay.
And those correlations would be imprinted on this shape of the two-dimensional function. Okay. All right. So that's easy. That's when the two photons are one photon is inside, one is still outside. And of course, inside we have more amplitudes that we need to follow. Those are coupled amplitudes, and you could write the coupled equations, and you can solve them numerically, and you can see what it does. And then those photons come out, and we detect the first one. Let's suppose that we detected the photons we called 1 at coordinate L at the end of the medium. And when we detected this first one, the remaining one needs still to leave the medium. So it has some dynamics when it comes out of the medium. And when it gets to the end, to its own L, we detect it with our second detector. Okay. So in fact, what we measure is those phi2 and G2, but and then we need to back propagate in order to understand what happened in here and what happened inside. That's kind of part of what we do. So what do we expect to see? So in general, photons come from here. They arrive at no correlations, Poissonian distribution. So that would be psi equals 1. These are the no correlation value. And then they mostly propagate along this diagonal. They both start from 0 and they end up in L. So the general dynamics is along the diagonal, the main diagonal. If the interaction between them is such that it's kind of a conservative dispersive interaction, it is such that they imprint a phase onto each other. One photon accumulates more phase in the presence of the other. That is one of the interactions we could think of. Then, when they are close together, which means along the diagonal, they will accumulate phase. Okay, so the phase that we will see on this wave function is 0 in the beginning, before correlations develop, and a finite phase at the end of the medium. And this we will call the conditional phase, measuring the phase of a photon conditioned on seeing another photon close by. In addition, as in every optical system, we have dispersion in our medium, as well as in, you could either engineer this, and usually it comes naturally. And dispersion in optics, as you know, is a k-squared term that has the shape of a mass term. That's kind of a usual analogy used in optics between the Schrödinger equation and optical dynamics. And so there would be something that generates correlations, and another term, a dispersion, that tries to smooth out those correlations. And as you already noticed, I wrote this as a potential and as a mass term, so kind of very naturally I get an effective Schrödinger equation, where instead of time, the position along the diagonal, this center of mass, plays the role of the dynamical variable, and the distance between the photons plays the role of space. And this indeed turns out to be a very good description of the system. It is the most coarse approximation, okay? So there are better approximations than that. And it is still describing many of the phenomena that we see. So what do we expect to see when we have a Schrödinger equation? And I'll show you one thing that happens when you have a Schrödinger equation that maybe many of you did not notice before about the abilities of Schrödinger equations. So this is the simplest Schrödinger equation you can think of. It's in one dimension, single particle, mass, and we use also the simplest potential we can think of, just a square potential well. And we start with the simplest initial state that we can think of, which is simply everything is one everywhere. Okay. So what would happen now when we run this equation in time? So of course, the parts of the wave function that are above the well will start to accumulate phase. That's what the Schrödinger equation does. And if we look at the phase, the argument of psi, we see that it accumulates phase. We also see that ripples appear on the probability, on the absolute value of psi, due to maybe, if you want, attraction into the well. And what happens if I continue? More phase accumulates. And it turns out that when this more phase accumulates, whereas on the far away part, the outer parts, nothing happens, we find 2 points in the space-time plane in which the amplitude is completely 0, and the phase does this 2-pi twist, clockwise and counterclockwise. We have a pair of phase vortices, field vortices, in this space-time plane. This, I don't know if you expected this or not, but this is not the only option that you could think of. If, for example, if it was a different type of a dynamical equation. Another option would have been that the fact that the center part propagates fast, the phase accumulates fast, and the outer part accumulates slowly, would simply mean that more and more of the inside accumulates phase, and it sends phase outside, and it tells the outside that there is some phase accumulated inside. But this is not what happens in here. Nature, or the Schrödinger equation, prefers to introduce these 2 dislocations and unwind the tension between the inside and outside, such that after some time, it gets back to no difference, to 0.
Did you find this like in a paper from whatever the?
No, not yet.
Really?
Yeah.
It's like it's just.
I can write a paper on that, yeah, or a textbook or whatever. Yeah, that's pretty crazy. Because we all learned the Schrödinger equation, the one-dimensional version, probably like in 8th grade, right? 9th grade. When do you teach this in the US? Yeah. So and we never noticed, or maybe Bill noticed. No. Not only that, but so we could explain this with the tools we know. So and every in one dimension, every potential well will have some bound state. This potential well could be very shallow, and it will still support at least one bound state, which I draw here in red. And if you think about the initial condition, which is in blue, you could decompose it into the bound state, and all the rest of the stuff that is unbound. The bound state will rotate in the complex plane in the rate that is associated with the bound state energy. And when it rotates, at some point in time, it will destructively interfere with the rest of the part. And this destructive interference is associated with these 2 vortices. This also means that in the next rotation, it will do that again. And we get a series of these vortices, and they never stop. They don't look exactly the same. They logarithmically diverge. And not only that, this turns out to be very robust. It doesn't matter how the well looks, if it's deep or shallow, if it's a delta function or some structure. You always get those vortices. Sometimes it's a series of vortices. Looks like a bit chaotic. Yeah, that's the negative part. Yeah. So what would happen if you flip the potential? Well, the same, but the opposite colors.
Now, when you say a vortex,
Yeah. No, it's a
it's a vortex in a position time space.
For now.
Not like.
For now, it's a vortex in a position.
That's not
right.
the usual vortex.
Yeah, that's not the usual vortex. No. Yeah. So optics people, I minus. Yeah.
Oh, if there are no bound states still, or like whatever.
There's
higher dimensions.
I don't know if there is no. I guess so.
Okay, but if it's delta function, separated vortices, right? Or is that?
No. If it's a delta function, there's still some scattering length associated with this bound state, and they will appear on the length scale of the scattering length.
Okay, but here with the square well, the zeros are at the edge.
No, not necessarily. No, I think they will appear somewhere here.
Okay, so
cool, huh? Yeah. So very, very natural. And I understand some of you have already seen this movie, but I'll show this again. So this is a real summer pool party we held with actually me standing there holding this surfboard, kids boogie kind of, and pushing the surface of the water pool. And what you see here is this movie plays in real time. And you already noticed these 2 circles rotating clockwise and counterclockwise. These are vortices, of course, of water. They are connected below the surface of the water with a vortex tube, half of a tube. This is also why they're so stable. And they continue. You can try this at home if you have a pool at home.
This reminds me very much of Feynman's treatment of the creation of vortices in superfluid helium by the opening of a tube into
Exactly.
reservoir.
Exactly. And the same physics, similar line of thought. There is some dissonance between the center part, which I pushed, and the outer part, which I didn't. And there are always two options how to resolve this. One is accelerate everything. The other is introduce something that undoes. And in 3 dimensions, this something that undoes this is a tube, is a vortex ring. Okay.
So how close is the connection to the photons?
Well, up to what you imagine.
So, like, the equations are not the same.
No, it's not the same. It's not the same. But both of them are quite robust.
Just the vortices here and there, like the equations.
Yeah, and also this is for you to be able to imagine a vortex ring created from this, because we are going to see this with 3 photons. There would be vortex rings appearing. That was the question, right? See?
Because there's time dynamics here in 2 spatial dimensions.
Yes.
Like 2 plus 1.
Yeah. So this will just simply will appear when we have 3 photons. Yeah. All right. I'll make use of this pause to thank the team and to acknowledge 2 people. So Banking visited here, I think 6 months ago, and also Sasha Pudabny, who's now we work with on the theory side. Okay. Kind of the end of the intro to the intro. I'll try to go a bit more slowly on several points now that I skipped. And one of them, I say interaction, and I introduced this psi, but we could use this definition of psi to define what the interaction means, what the strength of the interaction is. So I remind you, this is a Poissonian input to some state. Mostly we get zeros, and sometimes we get 1, and rarely we get 2. And epsilon here is a complex number that is simply proportional to the electric field. And these pass through the medium. If the medium has some linear optical response, I mark this with eta. Eta is a complex number that could represent absorption, scattering. And of course, 1 photon feels it, and also 2 photons feel it, and etc. If the medium is nonlinear, then there is another complex number, psi, that I only put here for the 2 photon component. Okay? So this is the extra stuff that happens to 2 photons that did not happen to single photons. And this psi quantifies for me how much nonlinear is the medium. And it is 1 if the medium is linear, and it is very different than 1 if the medium is very nonlinear. And this is what we call quantum nonlinear. So very different from 1 could be either psi 0. So this term never appears, which means that the medium only transmits single photons. And this we call dissipative interaction between the photons. And the other option is that the absolute value of psi is still 1, which means this term always appears, and the photons do not cause each other to not pass, but they do introduce a phase onto onto each other, onto the pair, and the phase of psi quantifies this conditional phase, and the ideal case would be pi. If this was a quantum gate for photons, and representing some deterministic interaction that realizes a gate, then the pi conditional phase would correspond to a maximally entangling operation. Okay, and this we would call a dispersive or conservative interaction between the photons. So the level that psi, the psi quantifies for us how much nonlinear the medium is. And as I said, we easily measure psi, so you could easily test that, check that what we call the G2 function, the ratio between detecting pairs and detecting singles, is exactly absolute value psi squared. And we could also measure the phase by building this interferometer, and we get the full value of psi versus the time separation between the photons. And we can generalize this, as we already saw, to a psi inside the medium. All right. How do we get those interactions to work for us? So as I said, we build those hybrid superpositions, hybrid creatures that are called polaritons, which are mutual excitations of a photon and an atomic level under these conditions of electromagnetically induced transparency, which I'm sure many of you know. In fact, we send our signal photons, the weak field that we work on here, exciting from the ground state to an intermediate state. And we always have present a strong additional field, with a drive or a control field that couples this intermediate state to the Rydberg level. And what happens then is that we have a superposition of photon and Rydberg that propagates. And when it is a photon, in this superposition sense, it propagates very fast in the speed of light. And when it is an excitation, an atomic excitation, and no photon, it is standing still. It does not move at all. And therefore, the speed of this creature is the ratio between how much this is a photon and how much this is a matter. And in our case, this is about 10 to the minus 6. So our polaritons propagate at 10 to the minus 6, the speed of light. And mostly when they are inside, they are a Rydberg atom. This is why two of them interact strongly and deterministically. And so if we put everything together, here is one photon inside exciting its own Rydberg atom. We can play with the detuning from the intermediate state in order to play with the flavor of the interaction. And if we add now another photon, and if they are close enough, then we bump into this effect, which many of you know. This is the Rydberg blockade effect. This means that for a strong enough interaction, the process of exciting a Rydberg atom is blocked, is forbidden, which means one photon can enjoy all of these polariton physics, but the other one is stuck here, exciting only in the intermediate state. And what this does to it, it depends on whether there is some detuning or not. For example, if the detuning is strong, then we see that it accumulates a phase that depends on the optical depth of this interaction range. In our case, the interaction range is about 15 microns, and the optical depth of this blocked blob is much larger than unity. So we can get very strong phases using this blockade mechanism. I want to skip a bit faster this slide, so allow me maybe. We play some trick where we tune the parameters to have a 3-level transmission and a 2-level transmission that is the same transmission. And this somehow eliminates most of the dissipative part of the interaction and leaves us only with the conservative part of the interaction. And then also, if you zoom in on the part where we work, you see that there is a very strong quadratic dispersion. So now we have our quadratic dispersion, and we have our conditional phase, and we put all of them together, and we get our Schrödinger equation. And if you quantify how strong the interaction is, one thing you could do, which you do usually in these strongly interacting systems, is you can compare the size of the kinetic energy to the potential energy. And in our case, this ratio is 3. So it's not a very strongly interacting system. This is not much larger than unity, but it is still larger than unity. There is a reason why it's in gray. So Q is a number between 1 and 2. That depends on how close you are between, where you are between the 2-level resonance and the Raman resonance. Okay. Now experiments. I'll show you some results now. This is how it looks in our lab. It's a standard cold atom setup with a very, very large glass cell. It's about 9 by 9 centimeters by 15. And then in the center, we have an elongated cloud. This cloud is about 75 microns long, micrometers long, and has a total optical depth that gets to 150, and very high atomic density, and therefore large optical depth of the blockade, for those who are interested. We also focus very strongly the light so that it's in one dimension effectively, and we measure the propagating photons on the other side. So we send them to the single photon detectors, and we measure correlations. Here are 2 examples for correlations. For example, this is anti-bunching. So Bill, this is how it would look in a 2-dimensional space, anti-bunching. And this is bunching. You can see that there is some peak along the diagonal. And you could also mix the light with a local oscillator with the same light that goes around the experiment in order to measure the phase, the bit notes. And if the photons do something to each other, then you would notice that the bit notes move when the photons come up close to each other. So that allows us to measure phi2. And if we add yet another detector, we can measure also G3 and phi3 and all of those correlations.
So is the anti-bunched situation, is that just reflecting the blockade?
Yeah.
So
That's the simplest way, yes.
how do you get the
The bunch? The bunching, for example, would be if you manage to get the blockade to only introduce a phase onto, one photon onto the other, then you get effectively a potential well, and potential well leads to bunching because it's kind of attractive. It's an effective attractive force between the photons.
You do that by detuning?
Yes, just by detuning.
Yeah.
Yeah. All right. So what do we see? So here is like a simple experimental sequence. You send photons inside, and you measure phi2. And in the same experiment, you get all of this range of time separations between the photons because we don't control the time separation; it's just laser light. And we see that when the photons come out together, they have a bit of a different phase compared to what they have if they are 1 microseconds apart. So in this case, we would say that the conditional phase is 1/3 of pi. And we also observe a very strong bunching that comes with it. If we crank up now the medium, we elongate the medium, we make it denser, so we increase the optical depth to exactly 75. That's exactly the point where two photons that come out together show a exactly pi conditional phase. Okay, it's actually cool to look at the data at that point exactly. As you can see, there are bit nodes for photons that are not together, which is on the outer sides. We have the bit node somewhere. And then for photons that are together, the crest and the valleys exactly shift compared to one another. So that would correspond to a pi phase. Now, what would happen now if I increase the optical depth even further, kind of elongate the medium, essentially? It should get more phase, right? So you could imagine how this goes down, maybe wraps to the other side. But this is not what happens, actually. Instead, we crank up the optical depth just a bit more, and then we see something like that. And in fact, it starts to unwind. Okay. And if you take all of these data plots and put them on one plane, so these are many, many different optical depths, you see this image that we got used to see. Phase accumulates for closed photons. It doesn't do anything for photons that are not together. And then we identify 2 points in here where the phase does this 2 pi and minus 2 pi phase twist.
You said that, but it is what happens. It goes down and it comes. Like you said, it's not what it does. Your color just goes like
right. So what I expected actually to see 4 years ago was something that is like an enlarged version of the red. So something that goes like that. The parts that are more than minus pi, you could claim that you could call them plus pi, but you could also unwrap and call them minus 3 pi, whatever. But again, that's not what happens, right? At 0, it does the obvious thing. No. The surprising thing is what it does here on the where the vortices are. Why? Yeah.
And this place where you're saying the vortices, this is a vortex in an even straight.
Yes, you're correct. That's not even a space. What is that? These are different experiments. No, actually, it's the same experiment. In fact, all of this data is from one experiment. It's not one cycle because we average, but it's one experiment in the sense that the medium starts with very large optical depth. And during the experimental cycle, the optical depth decreases. And because we do experiments in steady state, in fact, what happens here is that this changes gradually in time, like that. That's interesting. But I agree with Bill. This is even a more feature space. And therefore, let me show you now a real one. Let's go forward. So what we can do is we can calculate this, as I explained to you, outside, inside, 2 are inside, 1 is outside, And as maybe not surprising in the field that we do, we get something that is very, very similar to the experiment. The simulation, you kind of reconstruct even this structure. And what we can do with simulations as opposed to experiment is we can look what happens inside the medium. So when the medium is long enough, say here at OD 90, where the vortices already form inside the medium and we don't see them outside anymore. In the simulation, we can look at the inside part of the medium. And indeed, what we see is that there are vortices here now in this coordinate Z1, Z2. Okay. By the way, as I remind you, this is not a two-dimensional real space. This is Z1, Z2 are two one-dimensional, but at least now we have vortices in space coordinates. Okay, but we'll get there. By the way, by the end of the talk, if everything succeeds, there will be vortices in time real vortices.
But it's all essentially the same thing. That is time and space connected
yes.
as is optical depth.
I agree.
So it's really just a different way of applying it.
Yeah. Well, you see, after yeah. The criticism is in place still, I think. Yeah. No, I'm with you. I'm with you. All right. This is a nice short movie showing what happens if we send a pulse into the medium that depends on time, and how the vortices gradually penetrate. They come from the outer part, the far part of the medium, and comes in. I remind you, these are topological defects, so they either can be generated from each other. That's one option, or they can come in from the boundaries. They can pop up in the middle. In this case, they come from the boundaries.
The pulse coming
from here. Yeah, and the pulse comes from the left. The vortices enter from the right.
Where's the medium?
It's the circle. Yeah. The circle is the one standard deviation of the Gaussian medium. So now that we all understand 2 photons, let's go to 3. But don't be alarmed. 3 are just one more than 2. And in many ways, you see that the definition of G3 is as simple. We just add another detector. The problem is now that we don't have only one time separation in the pair, but we have 2 time separations, right? And therefore, we need a 2-dimensional plot for whatever was 1-dimensional before. So this is the separation between first and second photon, third and first photon. And what we do, we move to what we call the Jacobi coordinate system that kind of transforms the coordinates nicely so that all pairs are the same and born equally. So this is one of the permutations for a pair. That's another permutation with 6 permutations. This is how data look like. And now let's see those vortices. So for the same conditions that I showed you before, I now measure correlations between 3 photons. And you could see this here. So photons that are, a triplet where everything is far away, far apart, there is 0 phase, no interaction. All the pairs, which are in red here, accumulate exactly a pi phase. That's the tuning to here. And 3 photons that are together, which is the center, acquire 0 or 2 pi. Okay, and we can't exactly tell right now. All right, and this could depend also on optical depth as we did before. So it's a 3-dimensional space. You can cut it in all sorts of weird ways. We saw these vortices before for 2 photons, and now we see, if we compare, that for 3 photons there is a kind of another feature that does not appear in here, that is due to the 3rd photon puncturing a hole here through the 2 photons. And I know this sounds very complicated. So the easiest way to see this is to take this 3-dimensional space and run the MATLAB function isosurface on it, and then it looks like that. Okay, so then what you actually can see, this is all kind of data, just data, is the vortices that you got to know already for 2 photons. So the phase here twists clockwise and counterclockwise in each of these pairs, and it generates these lines. But in the center, there is a new feature, a ring, and this is a vortex ring. So if you cut it, you see the gradients of the phase along the ring. And this ring is associated with the interaction between 3 photons. And
so this parameter is less than so there's some creative transform from time variables?
No, so first, this is raw data, so no transforms in here. This is still just experimental data.
What is that?
Yeah, and then the third, the 2 axes are simply the time separation between the detection times. And
is there some causality that enters this? Because time is not kind of space. You're not supposed to know the future. So is it just creatively plotting stuff, which looks pretty, or there is so where is the fact that it's time as opposed to space? Where is the causality in this?
Yeah. So because there is no analysis yet and no somehow no processing, okay, there is still no need for causality explanation or something. This is just raw data. Now, because we measure outside, right, and if the medium is long enough, the vortices are inside, right? So the way you need to think about this is, if the medium is very, very short, nothing happens. Okay. And then we elongate it gradually until it becomes so long that vortices are generated inside due to this Schrödinger dynamics. Okay. This means that there is a length in which exactly those vortices are on the edge. And what we do is we cut. We look at these cross sections, and this is the third axis. Okay, these cross sections, and we see the structure of these vortices that are inside by somehow slicing the medium. Does this answer the question? In addition, let me just mention, and I hope to get there. When one photon leaves and it gets detected, other photons, maybe the second one or the third one, are still inside, and they still need to propagate outside, and there is still some dynamics that happens. So it's not a one-to-one correspondence between temporal shape outside and space shape inside. It's not simply translating by groove velocity or something like that. There are dynamics, and it's very complicated, in fact, and vortices move and come in and come out during this temporal propagation.
And it's always a weak pulse.
Yes.
That starts off as a coherent state.
Yes, yes. And this is kind of post-selecting on 3 photons, which is a very, very rare event.
So even the things that only indicate 2 photons are post-selected on 3 photons.
Yeah, no. So if we want to be dominated by pairs, we post-select on 2.
Yeah, but when you show that.
And we post-select on 3.
Okay, but they show the effect of 2s.
They show of course, yeah. Because if we post-select on 3, but one of the 3 photons was detected an hour ago, it's a 2-photon physics.
Right, but of course, an hour ago means.
Yeah, no, I mean,
the length of the pulse.
One microsecond ago. Yeah.
Oh.
10 microseconds.
Is it true that you're not in the dissipative regime and that's why there's no causality, but if you were in that dissipative regime, then you'd see that?
This is not I agree that it's strictly not, it's very, very not simple. Things happen during the propagation. There could be real time, even in the beginning, I could actually engineer the pulse to be, short, and there would be some temporal dynamics, which is not what happens in here because that's a steady state experiment. The pulse is very, very long. Right? Okay.
Well, when you say steady state, you mean 10 microseconds.
10 microseconds, yeah. An hour, 10 microseconds. Who counts?
Sure.
Yeah. Exactly, yeah.
The isosurface is the magnitude isosurface?
This is an isosurface of the magnitude of the gradient of the phase. All right, so you take a three-dimensional function, numerical gradient, absolute value, isosurface.
So there's a gradient phase connected to the velocity the way it is in.
Yes, why not? Yeah. No, for a vortex, the gradient of the phase is the velocity. Yes. And indeed, if you take an isosurface of that, you kind of cut a surface that has a fixed distance, like a definite distance around the core of the vortex. Yes.
Yeah. But all the stuff about time is just mapping space into time. I mean, there's no.
Yeah, well, these times were measured, so I don't. Yeah.
Sure, but it's.
All right. Yes. Let's do it. I'll skip that. I want to convince you that the ring is due to 3-photon interaction and the flower is due to 2-photon interaction. But I hope you're convinced. I know that people here also do some Kerr nonlinearity, so I just want to mention that after you extract the phase, the central part of this figure, the 3-photon phase, if you want, turns out to be 2 pi. Okay, so 2 photons acquire pi, 3 photons acquire 2 pi, which is not what you expect from Kerr nonlinearity. For Kerr nonlinearity, you expect 3 photons, which are 3 pairs, to acquire 3 pi, And this does not happen in our case. And simply speaking, this is because one photon blocks two other, but the blocked photons do not block each other now because they are blocked. Okay, so there's some regularization to the nonlinear phase for an increasing number of photons. Okay, and with this, sometimes I have remaining, I want to show you some highlights of kind of all sorts of interesting stuff. One thing is the effect of this shape, of the weird shape of our space, these boundaries where photons only start to interact when they are both inside. This fact is not captured by this simple model of the Schrödinger equation. Schrödinger equation has no kind of limited speed of information, and it's simply it's a very coarse approximation. It turns out that if you write the full model but stop just one step before when you get to the Schrödinger equation, in fact the system is better described by a set of linear equations that makes sense, where the number of equations equals the number of photons, and it has a linear dispersion relation. It's like a Dirac equation in the case of two photons. Okay, and this means also that instead of a parabolic dispersion, we need to somehow get a linear dispersion for large momenta, and this fixes this approximation. Has a proof. Here is the Schrödinger solution where things correlations should have not developed here because the two photons are not inside together yet, and for the Schrödinger equation they did, and for the real model they do not, for the dual model, which means this equation solves this problem. It also means that the formation of these vortices is somewhat delayed because it is pushed by the lack of interaction. So this looks negligible, but turns out that it affects the results when you put three photons together. And the reason is that for three photons, the volume is really complicated. It has all of those, two photons are inside, one photon is inside, all three photons are inside. This. And this means that we are living now in a cube. And this cube has a trigonal symmetry. It's not a circular symmetry like the Schrödinger equation assumes. And again, for the lack of time, let me skip that. These are simulations that we do, and you can see that the ring is not a circle, like a perfect circular ring, but rather it has this warped shape where some of the parts form earlier than others, because some of the parts have gone through more interactions. Two photons have been together and started the interaction before the third photon joined them and to the party. Whereas in the other case, it was only a first photon that came in, and the pair came in later on. And then we repeated the experiment, and we changed the analysis. And lo and behold, you could measure this. And what you see in here is the ring from the top and from the sides, and you can see this warping of the vortex of the three photon vortex ring due to this effect of the boundaries, which somehow closes a circle of things that Alexa and I worked on, so many years ago.
What changed? I thought you already saw that. Before it was a theory, like the ring you saw before.
No. So what? It's just a much better analysis with a kind of a way to reconstruct the optical depth with much better resolution. So we used that.
Which function ISO something?
It's the same.
Solve the data.
Yeah,
it's
the same. Yeah. I can no longer get the old data because I removed the analysis.
Does this impact any of these questions about causality then? Because the Schrödinger.
Well, you see the complexity of.
Less a non.
Yes, it does fixes a lot of the causality problem in that respect, of course. Yes. The Schrödinger equation has this problem where you quench in the center, you introduce this potential, suddenly everything knows about this quench. So this fixes it. That's one cool thing. I want to mention that we also do dissipative interactions, not only dispersive interactions. And because our medium is very long and strong, and we get a very long anti-bunching ranges. So here, for example, you send laser light in, and the laser light, the light that comes out is anti-bunched with a very long anti-bunching distance of half a microsecond. And this is determined, this half a microsecond is determined by the fact that the photons come in, and then they undergo dispersion, and but anti-bunching always happen, and dispersion widens this feature, and anti-bunching continues to happen, and dispersion continues to widen this feature. So at the end, the length of this anti-bunching, you see the broadening of this feature, is just due to the fact that the medium is very dispersive and it has a limited bandwidth, and this is the bandwidth of the medium. That was well known. What we did recently, so that's what you imagine if you send light in and there is blockade along the diagonal, you get this anti-bunching. Okay. What we recently did is we went to a different configuration. Instead of sending the two photons from the same side, we send them from opposite sides. And the way you should think about this is like that. The diagonal is still there, blockade is still there, but you send the photons along this direction now. One of the photons starts from the end and propagates backwards. And you can immediately see that this predicts that you would have a much larger anti-correlation range, much larger blockade range, which also closes another circuit. So we talked about this so long ago. And these are the data. So sorry for being a bit more quick. You could see that for counter-propagating photons, the anti-bunching distance is substantially larger compared to the co-propagating case. And if you quantify, sorry, let me skip. If you quantify this, you see that for the counter-propagating photons, the anti-bunching range scales with the length of the medium, which as you expect. But for the co-propagating photon, the anti-bunching range only scales with the bandwidth in the medium, so much slower. But this also means now, if you imagine this, the anti-bunching range, as the interaction range, this means that now, for the first time for us, the interaction range is larger than the bandwidth of the medium. And this means that if we now have pulses, we could manipulate pulses along the thought of manipulating quantum information. Suppose those pulses are qubits, and we want to manipulate these qubits. We have to have an interaction range that is as long as the bandwidth of the medium, so that the medium can accommodate those pulses, but still make them interact efficiently with high fidelity. And that's for the first time a condition that we reached, and this kind of is shown in here. So the pulses are those circles, and you can see that if we send them together, they almost here completely block each other. And there is this kind of sweet spot where the transmission is as high as the CW, and the interaction is strong. So that's what we wanted to get to. These are very preliminary things. Turns out that you get vortices also for counter-propagating photons, which is extremely surprising and has to do with some post-propagation. And because I showed you that, you already can read this map. Probably not very hard for you to read the three-dimensional version of this map. So somehow look like that. So you have a detector in here and a detector in here and another detector. So you see that there is a region here where you have one photon already detected, but the two photons are still inside and they interact. So things happen. And it turns out that you get all sorts of vortices. So these are vortices in space-space. This is a vortex in space-time. And this is a vortex in time-time that we expect now. We want to measure. This is only simulation, so we are kind of aspiring now to measure a time-time vortex. And a time-time vortex, which has a three-dimensional version, okay, is in fact a real vortex now in the quantum electric field of the light. So if we can get the light out, so not an internal vortex or a vortex in a fictitious space of OD versus something, but actually light that comes out with a quantum vortex inside, that would be very cool. And we think we have like a sweet, like a point in the conditions in which it should happen.
You're back to co-propagating.
Yes, but who knows? No, in fact, the counter-propagating vortices do not form inside, never. They only form outside. We don't know why. Yeah. All right, sorry. All right, so that's it. Thanks for listening. We do all sorts of other stuff, so whomever meets me, I'm happy to speak about everything. And thank you for listening.
Have the questions. You're amazing. You managed to finish this 5-hour intense to. See.
So, I mean, all your pictures first, you have zero L. In reality, you've got
The
a
Gaussian.
homogeneous Gaussian.
Yeah.
I presume that has very little influence.
Yeah, but not so much, it turns out. It indeed makes things just more complicated to analyze and understand. But calculating is as easy. In fact, it's easier to calculate Gaussian because you don't need to stitch any boundary conditions. And these are all calculated for a Gaussian cloud, for example. Yeah.
So you were describing these last ideas about the width of the anti-correlation of the
Light.
basically of the G2 hole. Now, so you described that in terms of bandwidth. What I was expecting you to say was that this has to do with the blockade radius and the velocity of propagation. Is it the same thing?
No, indeed. Blockade radius has a length scale of the distance, and then you have the groove velocity, which you can translate to time, and you get some number which is substantially smaller compared to what you measure. Again, the reason is, indeed, that would be what I would call the seed. But then this seed expands due to dispersion. And the seed continues and expands again, so it's a bit like a metal bar where you heat up in the center, but the size of the hot part eventually depends on the diffusion time. That's exactly the same thing here. There is some dispersion time or some bandwidth, and that determines the width that you measure.
The dispersion is related to the group velocity.
But not directly. It's
No.
the second order, the second derivative, and not the first derivative.
Sure.
Yeah. It's normalized by the groove velocity indeed. Right, Alexei? Yes.
Okay, but anyway, it's a different thing.
Sure. So I'm just wondering, so what physics here is specifically about photons as opposed to water waves or sound waves or whatever. So I can probably do it with, I don't know, just the sound wave propagating through. So
I guess so.
yeah, so like what's quantum about this thing?
The fact that we measure single photons and this space that we work in, being a two-dimensional space or a three-dimensional space, is not a real three-dimensional space or a real two-dimensional space, but rather it's the position of those single excitations.
Yeah, but I guess my question also is, I mean, it definitely looks super pretty, all these pictures, but okay, you plotted them and okay, great. So what do you do with this information?
I don't know, nothing, no.
More funding, get more funding.
Yeah. I do more experiments later. I agree. We don't yet find an application for the vortices, but I must say that we didn't expect these vortices. Our aim was to build a gate for 2 photons, and those photons, they don't want to be gated. And instead of getting a flat, nice pi phase over the whole photon pulse that will allow you to then build a new psi quantum, what you get is a pulse that has these 2 defects inside. The central part of the pulse has a pi phase, and the outer part has a 0 phase.
Is that psi quantum?
No, yeah. So these vortices are the opposite of an application.
Counter-propagating stuff.
Yeah, that's not bad. Yeah.
Last question. Let's see.
Okay, so following up on what Victor asked, which is what's quantum, your answer was, well, we're detecting photons. Well, people often have said that the detection of vortices in choose your favorite super whatever fluid conductor, cold, bose condensate is a hallmark of the quantum nature of the thing. But that has nothing to do with the fact that you're detecting single atoms.
No, it's in the mean field, you say.
It has to do with the fact you've got a coherent wave function.
Yeah.
So.
Yeah, I don't know how you could map this easily as in here into like a mean field, because again, those coordinates are coordinates in a second quantization sense. Then it's not a real space, so that's easy. That's hard to find an analogy, but I guess there are analogies. This is a bit akin to phase slips in a superconducting nanowire, by the way. That again is somehow penetrates sometimes and unwinds a 2 pi phase, kind of relaxes a 2 pi difference. It's a bit like that.
Yeah, and the thing that counts there is the fact that you've got coherence, so that it makes sense to talk about.
Yeah, I mean, without without coherence, maybe I cannot define a vortex. But again, I can take a fluid and then decide that the velocity. Yeah, yes, yeah.
I mean, your swimming pool wasn't.
Even a classical vortex. Yeah.
Okay, let's think. I'll forget about TT. There's T at 4 again, and 2117 for postdoc graduate students. So make sure to attend it. Thank you, guys. So what you need, right, is the interaction, right? You won't get those like long-range interactions.
You know my friend Yuval, right?